Welcome everyone to the last lecture of the course Statistical Model Selection for Stochastic Systems with Applications to Bioinformatics, Linguistics and Neurobiology. In this lecture, we'll be discussing about a general mathematical model to describe a network of neurons. Then, through an example, we will discuss what are perfect simulation algorithms. And finally, we will discuss some theoretical results, so theoretical guarantees for lasso methods for partially observed network of neurons, so under partial observation. So let's begin with general mathematical model to describe network of neurons. To describe the model, I need to introduce first some notation. So in what follows, the set I is going to be a countable set. So this is the set of neurons of my network. Neurons. And from now on, the elements of I will be called neurons. The network of neurons will be described in discrete time, and the time index will be the set of integers. So Z here is the time index, and the activity of the network is going to be described by a collection of random variables xit, where I is in the set capital I and t is in the set of integers. And in probability theory, we call such a collection a stochastic process or stochastic chain. And we will assume that this stochastic chain is stationary. So for each time t and for each neuron in the network, the random variable xit is a Bernoulli random variable, and it takes value 1 if neuron I spikes at time t and 0 otherwise. And what you see here at the bottom of the screen is just a piece of a realization of this stochastic chain. So on the x-axis we have time, and in the y-axis we have the neurons. So in this case we have I equals to 1, 2, 3, 4, and so here we can say that's neuron 1, here's 2, 3, and 4. So each row here represents a given neuron in the network. And if here is time t, the configuration of the network at time t will be the random vector xt here, and xt here is the random vector xit when we vary I in the set of neurons. Okay, so in this particular example, we have that x1t is equal to 0 and x2t is equal to 1, just to give some examples. Okay, now let us discuss the model assumptions. The first assumption is the following. Given the path of the network up to the time t, so given x minus infinity to t, so this is a collection of random variables xi with I in the set capital I and s is at most t. So given this path, the random variables xit plus 1 with I in the set capital I are independent. So this means that the neurons are conditionally independent given the past. And the second condition of the first assumption is that, so for almost every past little x, the distribution of xit plus 1 given that the past up to the time t is little x is a Bernoulli random variable, as I said it before, and the parameter of this Bernoulli random variable depends on the neuron itself and on the past x. So it's pi of x. To illustrate this first assumption, let us consider an example, again with I equals to 1, 2, 3, 4, and suppose time t is here. Then what the first item of assumption 1 says is that at the time t plus 1, so at the next time unit, we have 4 independent random variables, so xit plus 1 and x2t plus 1, x3t plus 1, x4 plus 1 are all independent random variables. And the second item of definition 1 says the following. If the path of the network up to time t is little x, and little x here is the configuration of zeros and ones inside this rectangle. So if the path of the network up to time t is little x, then each one of these random variables, which are independent, have a parameter which depends on this path. So more precisely, x1 t plus 1 given x minus infinity to t is equal to x. So this is a Bernoulli random variable in which the parameter depends on the neural one. So this is a function p1 of x. And just to give another example, let's say x2 t plus 1 given this same path is also going to be a Bernoulli random variable, but now the parameter is a function p2 of x. Okay? Before giving the second assumption, I need to introduce a notation. So for each space-time configuration little x, and any finite subset S of I times minus, we denote x sub x, the configuration x restricted to the subset of S. So more precisely, x sub S is the configuration xit, where the pair it belongs to the set S. To illustrate this definition, let us consider an example, again with I equals to the set 1, 2, 3, 4, so 1, 2, 3, 4, and let's say that the neurons are arranged in this way, so 1, 2, 3, and 4, and suppose that x, my configuration x, is this thing here, so x is here, and let's suppose that here is time minus 1, 2, 3, 4, 5, so let's say 5 minus 5 is here, and suppose that S is the set of pairs of the form 4 minus 1, 1 minus 5, 2 minus 5, and 3 minus 6. Then the configuration x sub s is the configuration inside these blue rectangles. Okay? With this notation, the second assumption of the model is the following. So let V be a collection of finite subsets S of I times Z minus, and for each S and for each I have a number lambda I of x, which is larger or equal to 0. And for each I and S, we have a function pix taking values in 0, 1. X here is a given path, so it's an element of 0, 1, I times z minus, and so this function pis of x is a function of x only through the configuration x sub s. So depends on the past only through the coordinates restricted to the set S. So what the second assumption says is that given the set V and given the numbers lambda is and the functions pis, the function pi of x can be written as a convex combination of the functions pis. More precisely, pi of x is given by lambda I of the empty set P of the empty set I of x plus a sum over S in the set capital V, S different from the empty set of lambda I of S times P S I of x, where the lambdas I satisfies the following: the sum over S in the set V of lambda I of S is equal to 1. Okay, so what does the second assumption mean? So remember that Pix is the probability of assigning a symbol 1 to the site I t plus 1, given that the past up to time t is x. Okay? So one way of interpreting this decomposition is as follows: to decide a value to the site I t plus 1, we first choose a space-time neighborhood in the set capital V with distribution lambda I, and then given this random neighborhood, so given this neighborhood, say S, assign a symbol 1 with probability PIS of x. Okay? To illustrate this definition, let's say that here is the past of the network up to time t. So this is equals to x. So this is the past. So here's time t plus 1. Let's say that this specific raw corresponds to neural I. So to the site I t plus 1, I have associated the random variable xi t plus 1. And so what this space-time decomposition says is that first I need to choose a space-time neighborhood in V. So to be concrete, let's assume that here is neuron 1, 2, 3. In this case, neuron I is the neuron 4. And so let's say that I have chosen the set S as the set 1 minus 1, 1 minus 2, and 3 minus 2. So this has probability lambda I of S. And given this choice of S, the probability of observing a 1 for x psi t plus 1 will be a function of the zeros and ones inside the blue rectangles. Okay, so this is the second assumption of the model. So let me make some remarks. So the first remark is the space-time decomposition that we just saw generalizes what is called in the literature Kalikov decomposition. And the Kalikov decomposition has been introduced by Kalikov in the 90s and has been further developed in a series of papers. And just to mention two, let me mention the paper by Comets, Fernandez, and Ferrari in 2002, where they present the Kalikov decomposition to chains of infinite order. And let me mention also the paper by Galves and Leonardi in 2013, where they consider Kalikov decomposition to space-time systems, as we are doing here, but their Kalikov decomposition is less general than the one that I'm presenting here. Okay? And with agreement with what I just said, examples of models admitting space-time decomposition includes the Markov chains, so this is an exercise in the book. It also includes chains of infinite order, and this is what Comets, Fernandez, and Ferrari presented in their paper. And in these both cases, the set I has cardinality 1. And the third example is the GL model, the GL neural network. And the third example is the GL neural model. So this model has been introduced by Galves and Leonardi in 2013. So that's why it's called a GL model. In this case, the set I is much larger than 1, and in fact can be even infinity. And the last remark is the notion of probabilistic sparsity. Let's say that I have a random variable vi with distribution lambda I, so distribution is over the space-time neighborhoods for neuron I, and then we will speak about probabilistic sparsity if the random set vi has size small with high probability. So if the distribution lambda I is concentrated in space-time configurations with very small sizes, then we speak about probabilistic sparsity. And the notion of probabilistic sparsity plays an important role in the theory that we present in this lecture. So let us discuss an example of a space-time model in which we can find very easily the space-time decomposition for the function pi of x, which is sparse in the sense that we just described. And the example is the following. For each x, so a space-time configuration of zeros and ones, and for each neuron, let us define psi I of x, which is the function nu I, plus a sum over s in the set z minus, a sum over j in the set of neurons I of age j goes to I evaluated at time minus s times xjs, and define pi of x as the function psi I of x if psi I of x is in 0, 1. Pi of x will be 1 if psi I x is strictly larger than 1, and psi I of x will be 0 if psi I of x is strictly smaller than 0. In the definition of psi I of x, the parameter nu I represents the spontaneous activity of neuron I, and to see this, x is a past such that xjs is equal to 0 for all j and s, then the probability of observing a spike to I given this path, so the I of x will be nu I. Even if I don't have any contribution of spikes of the other neurons, I still have a positive probability of observing one, which is nu I. That's why we interpret nu I as the spontaneous activity of neuron I. And the function age j goes to y describes the fact that a spike of neuron j has on neuron I after s time units. So one way of seeing this is, suppose that we have a past x, so this is a past x, and then I look at the jth raw of this past and the ith raw of this past. So here is time minus 1, and say here is time s. And for this specific past, I have x, j, s equals to 1. So meaning that neuron I has spiked at s time units in the past, then the contribution of this spike to the probability of observing a spike for I at time 0, which is going to be a function of j and I. So age j goes to I, evaluated at minus s, because the spike of neuron j was s time units in the past. So this distance here is minus s. So this explains the definition of the function psi I of x. So let us compute in this case which is the space-time decomposition for pi of x. So to do so, for each I, for each neuron, let us define the set AI plus, which is the set of pairs JS, such that age j goes to y of minus s is positive. So this set we'll call excitatory set. And similarly, we can define the set AI minus, which is the set of pairs J and S, in which the age, so here age J goes to I of minus S is strictly negative. So this is the set of all pairs in AI minus. And for this reason, I call this set inhibitory set. So with this notation, let me also define sigma I plus, so this is the sum over all pairs JS in AI plus of age j goes to I evaluated at minus s, so there is an absolute value here. And similarly, I can define sigma I minus, where I replace here AI plus by AI minus. With this notation, let me also assume that Vi minus sigma I minus is larger or equal than 0, and also that Vi plus sigma I plus is smaller or equal than 1. And under these conditions, we know that Pi of x is actually equals to psi I of x for all x and I. So under these assumptions and with this notation, we can compute very easily now the space-time decomposition for Pi of x. So how do we do? So Pi of x. So how do we do? So Pi of x, which is psi I of x. So this is nu I plus the sum over j in I, sum s in z minus, of lambda j goes to I of minus s xjs, right? Now I sum and subtract sigma I minus. So I have here nu I minus sigma I minus plus the sum of all pairs j and s belonging to ai plus of h goes to I of minus s x js. So here, for the pairs j and s in ai plus, I can put an absolute value here, and then I have also plus the sum over j and s in ai minus of hj goes to I of minus s times x js. But now, if I want to put absolute value here, I can do it, but then I need to put a sign of minus in front. And since I have subtracted here sigma I minus, I have to add it. So the definition of sigma I minus is the sum over j and s in ai minus of the absolute value of h j goes to y of minus s times 1. So I can actually rewrite these two terms as follows. So I can erase this and also x here. So I have 1 minus xjs, but now I have a plus here in front, okay? And now for each pair js in ai plus, I will write p of the pair js, so here's a set, I of x is going to be xjs, and similarly for pairs js in the set ai minus, I will denote pi of the pair x, so pi of js at x is going to be 1 minus xjs. And then, if for each pair j and s I denote the absolute value of h j goes to y of minus x by lambda I of the set js, then we can rewrite pi of x as nu I minus sigma I minus plus the sum over j s belonging to ai plus union ai minus of lambda I of the set js, so the unitary set with the pair js, times pi of the unitary set sj of x. And now, to actually conclude the example, you just need to observe that if lambda I of the empty set is equals to 1 minus sigma I plus sigma I minus, and pi of the empty set is nu I minus sigma I minus divided by lambda I of the empty set, then this last term here is lambda of the empty set times pi of the empty set of x. And so in this way, we ended up computing exactly the space-time decomposition for the pi of x of this example. So to sum up, what we have shown is that for this precise example, pi of x admits a space-time decomposition where lambda of the empty set is 1 minus sigma I plus sigma I minus p of the empty set of I is I minus sigma I minus divided by lambda I of the empty set. Lambda I of the set which has only the pair Js is given by the absolute value of age j goes to I of minus s for all pairs Js which are in the union of ai plus with ai minus, and for each pair j and s in the ai plus, the function pi of the corresponding pair of x is just the value of xjs, and if I take a pair j and s in ai minus, the pi js of x is 1 minus xjs, okay? And of course, to have the quantity pi of empty well-defined, we need to impose that the sum of sigma I plus with sigma I minus is strictly smaller than 1. And then in this case, lambda I of the empty set is strictly positive, so this ratio here is well-defined. So here, in this case, we have probabilistic sparsity, so that's why we say that pi of x admits a sparse space-time decomposition, because the space-time neighborhoods of I have all size 1. Okay, so this is a very interesting property of this model. And a second interesting property is that if I take a pair Js which is in the excitatory set, okay, which is in the excitatory set, then the corresponding function pi of x is just xjs. So I'm copying exactly the value of the pair js. And now, if I take a pair Js, which is in the set ai minus, what I'm doing here, so the function pi of x of the corresponding pair is going to be 1 minus xjs. I'm flipping the sign that we had in the pair Js, okay? So this is a very nice description of the model. So now let us discuss through an example what are perfect simulation algorithms, okay? And our toy example will be the previous one. In a very few words, a perfect simulation algorithm is a probabilistic algorithm which allows us to simulate from the invariant distribution of the process, and this is very useful, especially in the case in which we don't know exactly the expression for the invariant distribution of the process. And an interesting property is that usually you can implement perfect simulation algorithms on a computer. In the book, we have presented perfect simulation algorithms for general space-time systems in which the functions pi of x are sufficiently sparse. In this lecture, for time constraint, we will focus on a particular sparse space-time model, which is the Hawkes model. So the goal is to simulate the variable xit for a given pair it where I belongs to the set of neurons and t here is a time index in the set z. Okay, and I want to simulate xit under the invariant distribution. So what is the algorithm? So algorithm algorithm. The algorithm has 4 steps. The first step is the following. Step 1, choose VIT, so this is a random variable with distribution lambda I. So lambda I is a distribution of the space-time neighborhoods for neuron I at time 0, and define the set AIT1 as the empty set if VIT is equal to the empty set and JT plus S if VIT is equals to JS with J in I and S in Z minus. And again, what we are doing is that first we choose a space-time neighborhood for neuron I at time 0, and then we are shifting it to time units. So this is the first step. Now let us talk about this step 2. So step 2, for all n larger or equal than 1, define recursively the set AIN plus 1 IT as follows. If ANIT is equal to the empty set, then we define AN plus 1 IT as the empty set as well. Otherwise, say INIT is a given pair S and J. In this case, what we do is we choose VJS using the distribution lambda J and define the set AN plus 1 IT as the empty set if VJS is the empty set, and AN plus 1 IT is going to be the pair K S plus H if VJS is equals to the pair KH. And this is in I times Z minus. So before going to the step 3, let us introduce some notation. So let NIT, so is the first time such that the set AITN is the empty set, and define what we call the genealogy to generate the random variable xit as the union of A and IT with n going from 1 to NIT. And with this notation, we have from proposition 512 in the book, applied to this particular case, the following result. If the supremum over I in the set capital I of the sum J belonging to the set I, sum S belonging to the set C minus of H goes to I of minus s absolute value is strictly smaller than 1, then the probability that NIT will be finite with probability 1, and this holds for all I belonging to I and T belonging to Z. And what proposition 512 is telling us is that if the sup of this double sum of the absolute value of Wj goes to y evaluated at minus s is strictly smaller than 1, then with probability 1, the genealogy to simulate the random variable xit, that is the set git, will be finite, and as we'll see in a moment, this ensures that step 3 of the algorithm is actually well defined. So before going to step 3, let me do a very quick remark, is that this condition here is equivalent. So this is equivalent to the infimum over I in the set of neurons of lambda I of the empty set is positive. Okay? So it's telling us that if uniformly over the set of neurons the lambda I is strictly positive, then the set GIT will be a finite set. Okay? Now let us define the step 3. So step 3. So what do we do in step 3? So if NIT is equals to 1, that is A1IT is the empty set, then let UIT be a uniform random variable on the interval 0, 1, and define xit as the indicator that this uniform random variable is below pi of empty set. So in other words, in this case, xit will be equals to 1 with probability pi of empty set, and will be 0 with probability 1 minus pi of the empty set. Okay? Now, if NIT is strictly larger than 1, and in this case, observe that if JS is equals to the set AIT NIT minus 1, then by the definition of NIT, we know that the set VJS is going to be the empty set. So then we generate a random variable UJS, which is uniform. All the uniforms are independent, and define the random variable xjs as the indicator that this uniform random number is smaller or equal than p empty set of j. So in other words, in this case, we know that if js is the set AIT NIT minus 1, and so in this case we know that VJS is going to be the empty set. So this means that the random variable xjs will choose a symbol 1 or 0 independently of everything else, and the probability that xjs is going to be 1 is pj of the empty set, and the probability that it's going to be 0 is 1 minus pj of the empty set. And this completes step 3. And finally, let us define the last step, which is step 4. So step 4, generate recursively uniform random variables, all independent, for J and S equals to ALIT, and here L, so for L going from NIT minus 2 to L equals 1, and if AL minus 1 IT is equal to, let's say, KS plus H, then XJS, the random variable associated to the pair JS, which is equal to ALIT, is defined as follows. So it's going to be XKS plus H if the pair KH is excitatory for J, and is going to be 1 minus XKS plus H if the pair KH is in the inhibitory set for J. Note that at L equals 1, we have that XIT is going to be XJS plus T if the pair JS is an excitatory pair for neuron I, and is going to be 1 minus JS plus T if JS belongs to the set of inhibitory pairs for neuron I. And this concludes the algorithm. So let's have a look in a picture just to understand what we did mathematically. So here we have a picture to illustrate a realization of the algorithm that we just described. Okay, so here I have neuron I at time t, and what we want to do is to simulate XIT, right? So what the algorithm does is the following. So first, I need to choose a space-time neighborhood for neuron I at time t. So let's say that I have chosen the pair J at time t minus s. So it's this guy here. And so this means that A1 of IT is the pair J t minus s. Okay? Then we continue, and for this pair here, I choose, let's say, a space-time neighborhood which is K t minus s minus h. Okay, so it's this guy here. And so this means that the set AIT2 is going to be K. So this means that the set A2IT is going to be K t minus s minus h. Okay? And let's say that in this particular example, the space-time neighborhood for neuron K at time t minus s minus h is the empty set. So this means that A3IT is going to be the empty set, and NIT, in this case, is going to be 3, okay? And note that in this example, I can write A2IT as a NIT minus 1 IT. And so this is essentially the step 1 and 2 together of the algorithm. And then what I do is recursively, now going forward, I will sample a value for this guy here, and then for this guy here, and finally for the pair IT, which is what we want to do, okay? So here, since the space-time neighborhood is the empty set, what the algorithm says is that I need to choose a value for xk t minus s minus h independently of everything else, and the probability of assigning a value 1 here is going to be p, the empty set k, and the probability of assigning 0 here will be 1 minus p of the empty set k. This step here is random. And then very interestingly, we will assign a value for xj t minus s, so xj t minus s is going to be the value that we just defined for xk t minus s minus h if this guy here is an excitatory for the site j t minus s. And the value that we will assign here for the site j t minus s is going to be 1 minus the site assigned here if this site here is inhibitory for this site here. And this is exactly what is defined here. Okay? And now that I have chosen a value for this site here, and then I know how to assign a value for this guy here, then I do the same analysis to define the value for xit. So if this guy here is an excitatory pair for neuron I at time t, the value that's here, I will copy it and paste it here. And on the other hand, if this pair here is inhibitory for neuron I at time t, the value that is here, I will flip it and then paste it here. And this is how the algorithm works. So we go backward up to a given site at which we choose independently a given value, and then we go forward assigning either 0 and 1 by looking if the previous site is inhibitory or excitatory for the next site. Okay? And what is very surprising is that by running this algorithm, at the end we sample xit from its invariant distribution. I will not prove this result, and if you want to know more about perfect simulation algorithms, please go and have a look at the references that we provide in our book. To conclude this example, let me just make a very quick remark that is what we call the time length of the genealogy to simulate xit is this distance here in this case. Okay, so this is time length of the genealogy GI. So to sum up what we have seen about perfect simulation algorithms is that they allow us to simulate exactly from the invariant distribution of the process, and it applies to very large networks as we saw here in the Hawks model, as long as the condition of proposition 512 holds, which is highlighted here. And also something that I won't discuss in this lecture, but this is discussed in detail in the book, is that by studying the time length of a genealogy, one can actually establish classical concentration inequalities for these space-time models, and this is very useful, as we will see when we discuss about lasso methods for partially observed network of neurons. To conclude this lecture, let us now discuss some theoretical guarantees for lasso methods under partial observation. As many of you might know, lasso here means least absolute shrinkage and selector operator. And this method has been introduced by Robert Bischirani in the 90s in the context of regression analysis, and perhaps is one of the most used methods in statistics and even in machine learning. So essentially what lasso does is variable selection. And just to say a few more words, consider the linear regression framework. So we have y, which is n times 1, so this is a vector of dimension n, and this vector y is given by x times beta, where x here is a matrix n times p, the vector beta is p times 1 and plus some random noise, so this is n times 1. And one of the questions that one might ask in this setup is which are the non-null coefficients of the vector beta, and so we want to select which are the non-null coefficients of the vector beta. And this question is particularly interesting when p is much larger than n. So we are in the high dimensional case, meaning that the number of possibly non-null coefficients, which is p, is much larger than the sample size, which is n. And one of the main reasons that the lasso method became very popular is that it's able to solve this question in this high dimensional setup. So it's able to correctly identify the non-null coefficients of the vector beta. And if you want to know more about lasso methods in the regression framework, I really recommend you to have a look at the book by Mainwright, which is called High Dimensional Statistics, a Non-Asymptotic Viewpoint. In what follows, we shall see how to apply the lasso method to the problem of estimating the function pi of x for some I in f, so for a given neuron in the set f, from a sample xf from time minus m minus 1 up to t. So we observe a space-time configuration of zeros and ones, where the space component is f, and the range of the time component is from minus m minus 1 up to t, and we want to estimate the function pi of x from a given I in the set f. Okay, so if you want, you can really think of the sample as a matrix whose entries are either 0 and 1, where this matrix has f cardinal of f rows and m plus t columns. One of the challenges of this problem is that usually the size of the observed network of neurons, so cardinal of f, is large compared to the time units in which this network is observed, so t in this case. So we may say that the cardinal of f is large compared to t, so t is small in this case. So we are talking about a f large, t small problem, and this is the high dimensional version of our problem. Another challenge here is that usually we have partial and even very scarce observations, in the sense that the number of neurons in the network is d, and this number is much larger than the number of observed neurons. So what are the key ideas? So the first idea is that we want to approximate pi of x by linear combinations of pre-chosen functions. So these pre-chosen functions is what is called dictionary. The second idea is that only a few coefficients in this linear combination are non-zero. And finally, these pre-chosen functions depend only on xf from time minus m to minus 1. So in other words, the functions in our dictionary may take a space-time configuration where the space variables are in the set of f, in the set of observable neurons, and the time range here, so here is space, and here is time, and the time range here has size m. So the functions that we consider in the dictionary take into account what happens in a configuration where the space coordinates is f and the time range has size m. Okay, so this is a sequence of zeros and ones. And functions of this type is what we call in the book cylindrical. Okay, let us define formally what we mean by a dictionary. So a dictionary is a set phi, capital Phi, so it's a set of functions phi1, phi m, such that for all functions in my dictionary, this function takes a configuration of zeros and ones in I times in minus and gives us a real number which depends, so this is a cylindrical function, which depends only on xf from time minus m to minus 1, okay? So the time range has size m. And in the setting that we consider, the candidates to estimate pi are linear combinations of the functions in the dictionary, so are functions of the form, so the candidates to estimate pi of x are the form fa of x, which is a linear combination, so it's a sum over j going from 1 to m of aj times phi j of x, with a here a m-dimensional vector. Okay, and to give an example, so this is the example 524 in the book, which we call truncated Hawk's dictionary without spontaneous part. This truncated Hawk's dictionary is of the following form. So the set phi, capital Phi, is the set of all functions phi j s with j in capital F, and s here is from minus m to minus 1, where phi j s of x is just the projection of the space-time configuration in the coordinate js. So phi js of x is xjs. Okay, so this again, j is in f and s is from minus m to minus 1. And in this case, you can check that the function fa of x is given by a sum of j with j in f, sum of s from 1 to m of aj minus s times xjs. I hope you can recognize that this looks like the Hawk's model that we considered earlier in this lecture, but now we are summing just over the observed set of neurons, and the time range has size m, and also we don't have here the parameter nu, I, which would correspond to what we call the spontaneous part. So we don't have this, that's why we call this dictionary truncated Hawk's dictionary without spontaneous part. With this dictionary, what we want to do is, okay, we take our space-time model, let's say the Hawk's model, and we want to approximate pi of x by a function of this type. The idea is that we want to select the coefficients aj minus s, which best approximates the pi of x. Okay? In this example, the size of the dictionary, which is m, is equals to cardinal of f times m. And observe that the functions phi j s are cylindrical because they depend on the neuron j's in f and times s between minus m and minus 1 only. Okay? So now let us define the lasso estimator of pi. So the lasso estimator of pi is defined as the function f hat, which is given by f of a hat, where this coefficient a hat, so this vector, minimizes some function, and this function is the sum of the least square contrast of fa plus a L1 penalization term. And the parameters lambda and d are positive and will be chosen later on. So just to gain some intuition, let's have a look at the least square term. What this term is doing is the following. I take some vector, m-dimensional vector A, and for each time t, by using the past of the network from time t minus m up to time t minus 1. And of course, I'm using all the information inside F. So what I do is that for each time t, by using the space-time configuration available at that time, I try to predict xit, and then I take an average with respect to time. So what this first term is doing is trying to find the best coefficient A to predict the sequence of spikes for near I. And the second term, so this is classical, this is L1 penalization, forcing us to have only a few coefficients non-zero. One can verify that a hat, as I define, can be computed as the argmean over A in Rm, so here, should be M, of minus 2A transpose B plus A transpose GA plus gamma D times the L1 norm of A, where B is a m-dimensional vector given by 1 over t, sum of t, small t going from 1 to t of phi j of the corresponding configuration, xf from time t minus m to time t plus 1 times xit. A transpose B is just the sum over j from 1 to m of a j times bj, so this is the Euclidean inner product. And G here, so G here is a matrix M by M called Gram matrix, and it's given by, so if I look at the entry JK, so the entry JK is 1 over T, the sum from T going from 1 to capital T of phi j of the configuration xf T minus M to T minus 1 times phi k evaluated at the same configuration. Okay, so this you can check, and perhaps this expression here is more similar to the classical version of lasso. Okay, and before moving on, let me mention an appealing property of the lasso, that is, it is defined through a minimization of a convex problem. Okay, so this is a convex minimization problem, and as such we can use techniques from convex optimization to approximate solutions to this problem very efficiently. And a second appealing property of the lasso is that we can, under some assumptions, prove that the lasso is almost as best as possible. So to formalize this idea, let me introduce some notation and definitions. We call f bar s the s-sparse oracle if f bar s is a linear combination of the functions in the dictionary, where the coefficients of this linear combination, so the vector a bar s, is the argmean over A in Rm, such that the vector m has at most s non-null coefficients, so Sa here is the set of all non-null coefficients of A, which is called the support of A. So As bar is the argmean over this subset of a function which looks like L2 norm. So here is Fa minus Pi norm 2 sub t. So this quantity here is defined as, so this quantity is defined as 1 over t, sum of t going from 1 to t of Fa of xf from time t minus m to time t minus 1 minus pi of the past of the network up to time t minus 1 to the square, so it's the difference to the square. So this is the definition of f bar s, and y is called oracle because this term here is unknown. Okay, so we would need to have an additional information in order to compute f bar s. And the S-sparse oracle we may interpret it as the best we can do in terms of L2 distance if we are allowed to use at most S non-null coefficients. So with this definition, one might ask under which conditions the F hat, so the lasso estimator, performs as good as the oracle F bar S. And this depends essentially on some properties of the Gram matrix G. And typically, one tries to show one of the following properties. Either you try to show that your matrix G satisfies what is called the inf kappa property. So this says that A transpose G times A is larger or equal than kappa times the L2 norm squared of A for all A in Rm. And this property is essentially saying that the smallest eigenvalue of the matrix G is kappa. Or one tries to show that a weaker property holds called Re kappa Cs property. So this is restricted eigenvalue property. And this property says the following: for all subsets J, so this is a subset from the set 1 to M, such that the size of J is at most S, and for all A in Rm, such that the L1 norm of the coordinates of A restricted to the set J complement is at most C times the L1 norm of A restricted to the coordinates in J. Okay, so for all such subsets J and all such vectors A, we have that A transpose G times A is larger or equal than kappa times the L2 norm squared of the vector A restricted to the components of J. So here J is a subset of 1 to M with cardinality at most S, and Ij is a vector such that Aj is equals to Ai if I belongs to J and 0 otherwise. And here, if you never saw this Re condition before, the vague idea is that the Re property is asking that the inf kappa must hold not for all vectors A, but for a well-chosen subset of vectors, the vectors satisfying this property here. To conclude this lecture, let us discuss some theoretical results. So this result is theorem 527 in the book, and it says the following: let gamma be larger or equal than 2, kappa is strictly positive, and S a natural number, on the event on which 1 bj minus b bar j is smaller or equal than d. So remember here that bj is the vector defined as the sum of t going from 1 to capital T of phi j x f t minus m to t minus 1 xit, so all this divided by 1 over t. So this is bj, and b bar j is almost the same expression, except that I replace xit by pi of the path of the network up to time t minus 1. Okay, so the first condition says that if the distance between bj and b bar j is smaller or equal than d, so for all j from 1 to m, and 2g satisfies the ER property with kappa, C of gamma, and S, where this C of gamma is this quantity here, so gamma plus 3 divided by gamma minus 2, Then we have the following oracle inequality. So the equality says the following, that the L2 distance between f hat and pi is smaller or equal than the L2 distance between the S sparse oracle and pi plus an error term. So this is saying that the lasso estimator under these conditions performs almost as best as the S sparse oracle. And this term here can be interpreted as an error term and what is important here is that it grows linearly with S, so the number of non-null coefficients that you want in your linear combination depends as 1 over kappa, where kappa here comes from the ER condition, depends as d square, where d here is the upper bound appearing in the condition 1, and depends on gamma as gamma plus 2 to the square over 4, where gamma here also appears in the definition of the ER property. And a remark here is that EV kappa corresponds to the ER condition when gamma is equals to 2 and S is equals to capital M. So in this case, the error term becomes 1 over kappa m d squared times 4. Theorem 527 is very interesting, but to apply it for a given dictionary, one needs to answer the following questions. The first question is, how do we choose D and M? And more importantly, how kappa depends on the number cardinal of f of observed neurons. To answer these questions, concentration inequalities, as the ones discussed in section 5.3 in the book, are fundamental tools. So let us first discuss how to choose D. So this result is also contained in theorem 527. How do I choose delta? For any fixed delta in 0, 1, I can take D, which is D of delta, where D of delta is the square root of the subnorm of the dictionary to the square times log m plus log of 2, 1 over delta, and this sum divided by 2t. So if I choose d of delta like this, then the probability that there exists should be j here. So the probability that there exists j in 1m, such that the difference between bj and b bar is strictly larger than d, is smaller or equal than delta. And in the above theorem, the subnorm of the dictionary is defined as the maximum over j from 1 to m of the subnorm of the function phi j. And just to have an example, let us apply this result to the truncated Hawks. So in this case, you can check that the subnorm of the dictionary is 1. Remember that m is small m times cardinal of f, and so in this case, the d delta is square root of log of small m plus log of cardinal of f plus log of 2 over delta divided by 2t. So here an important remark is that d delta will be small as long as the log of the number of observed neurons plus the log of the time range is small compared to t. And here I'm forgetting about the delta, which we can always control with respect to t, in the sense that delta can go to 0 slowly in such a way that log of 2 over delta still will be small compared to capital T. Okay. So to conclude this lecture, let me give you an interesting result which answers the question of how the kappa depends on the number of observed neurons for the case in which the network of neurons is given by the Hawkes model. So all that I'm going to talk about next holds for the Hawkes model. So the result is theorem 535 in the book, and it says the following. So assume that there exists theta strictly positive such that the supremum over I of the sum over j and s of E theta s times the absolute value of h j goes to y of minus s is strictly smaller than 1. So this says that the time length of the genealogy is sufficiently short. Okay, assume also that pi of x is larger or equal than mu, smaller or equal than 1 minus mu for some mu. So this condition is saying that the probability of observing a spike for I, no matter the past, will be always at least mu and at most 1 minus mu. So under these conditions and for the Hawkes model, then the Gram matrix associated to the dictionary of the example 524, so the truncated Hawkes dictionary without the spontaneous part, satisfies the ER condition for any gamma larger or equal than 2, S smaller or equal than M times cardinal of F. So this is M in this case, okay, with kappa equals to mu minus mu squared minus a product of 1 minus 2 mu plus RT and 1 plus C gamma times S, where RT is equals to C1. So C1 is a constant which depends only on the distribution of the Hawkes model. So C1 divided by square root of T times the square root of M plus log T plus log of cardinal of F times the square root of log M plus log of cardinal of F plus log 1 over delta, and there are a condition with gamma and S and kappa, as I just described, holds on an event which has probability at least 1 minus C2 over T minus delta, where C2 is also a constant which depends on the distribution of the Hawkes model. Okay, and so why this result is interesting? So it's interesting because it's saying that if the time range M and the number of observed neurons grow slowly compared to T, capital T, in such a way that this term RT is small, then the constant kappa does not depend at all on the number of observed neurons. Therefore, the error term in theorem 527 is not worsened by a huge number of observed neurons. And this is a drastic improvement with respect to previous results of Lasso in the context of a network of neurons. And to have kappa positive, what we need is that for each fixed C gamma and S, I need to take mu sufficiently close to 1/2 and to have the constant kappa here positive. For each fixed C and S, what we need is to take mu sufficiently close to 1/2.